So we have our cubic, we have our derivative, critical values, set it equal to 0, or look for places it doesn't exist. Now, this is a polynomial. Polynomials exist for all real numbers, so we don't have any of those problems there. So setting this equal to 0, I can see I could divide both sides by 3 to simplify this. So I get x squared minus 2x plus 1 equals 0. And that looks like it factors as x minus 1 times x minus 1. So I have a repeating factor here. So x minus 1 equals 0 means x equals 1. So x equals 1 is a critical number. So then I'm wondering is, if we focus on that x equals 1 here, what's happening with the slopes on either side? Right, so what is f prime of 0? What is f prime of 2? And let's see, if we check those out here, f prime of 0 is 3. That looks pretty easy. F prime of 2 is a bit more work, so that would be what, 3 times 4 minus 6 times 2 plus 3. So that's 12 minus 12 plus 3. Hey, that's 3. Wait a minute. That's positive and positive. Did I make a mistake? Is this increasing on each side? Huh. So this critical value doesn't look all that critical. Let's take a look. And I think I'll switch to GeoGebra just for fun. Of x equals x cubed minus 3x squared plus 3x plus 2. All right, so here's my function. We discovered that x equals 1 is a critical value. So I have that point right there. And it looks like the function increases into it and then increases out of it. So it looks like the slopes on the left are always positive, and the slopes on the right are always positive, but right in the middle, we have that 0 slope there. Right in the middle, we have a 0 slope. And we can double check that by putting in our derivative function. 3x squared minus 6x plus 3. And we already know, at least we believe from the work we did a minute ago, that if we plug in 0 there, we get, or not 0, but if we plug in 1 there, we get a 0 slope. And I don't really need to see the derivative function, I just want to use it. See x equals 1. So we have a 0 slope there, right? So we can double check with the tangent line there, y minus f of 1. Let's see, 0 slope equals 0. There's our tangent line there. All right, so point of this one right here is that just because you have a critical value doesn't mean you have a max or a min. You got to do further testing. Could you look at the graph and just say, oh yeah, it looks like it? Well, yes and no. I mean, it could be you just didn't zoom in enough on that to see that it maybe wiggled in there a little bit somehow, that there's not something weird going on. So just looking at the graph isn't sufficient. We need a little more evidence. And my extra piece of evidence here was I found slopes on each side of that critical number. I did double check to see, is it really true that f prime of 1 is 0, and that did check out. So I do have a 0 slope right here, positive slopes on the right, which means increasing on the, on the left, positive slopes on the right, so we're increasing on the right also. So we're just increasing right through there. Happens to have a instant flat spot, but otherwise it's always increasing, except at that point right there. All right, next one. Is f of x to the power, f of x equals x to the power 2/3. So before we do anything, let's find the derivative. F prime of x is equal to 2/3 times x to the power 2/3 minus 1. 2/3 minus 1, 1 is 3/3, that would be negative 1/3. Negative exponent really means flip the base. So this is 2/3 times 1 over x to the 1/3 power. And since x is in the denominator now, x cannot equal 0. So what do I know here? I know that at f prime of 0 does not exist, which means x equals 0 is a critical number. For 2 reasons. 1, f prime of 0 doesn't exist, and 2, f of 0 does exist. It is 0, right? That exists up there. So something interesting is going on when x equals 0. Let's take a look at the graph. Let's see if I can just, let's get a new one. Let's go back to Desmos. So f x raised to the power 2/3. Ooh, that's a cute one. And the derivative, the derivative is 2/3. I'm going to write it the first way I had it, which was x raised to the power -1/3. Oops, third. There we go. And we can see this function is in 2 pieces. It's broken, and it looks like we have negative slopes on the left, and we can kind of see that, right? This is decreasing on the left side, increasing on the right side. So we're going from decreasing to increasing, and then we have this weirdness going on in between here. And we'll explore this more later in a different section, but I just want to do a quick, let's make a point, an x value called c, and we'll let c equal -2 to start with. And then we're going to do a point, c comma f of c. So I'm just kind of doing the same setup I did earlier. And then through that point, I want to know what the slope is. I'll do an m equals d of c. Plug in the derivative to get the slope. We can see we got a negative slope there. And then the tangent line, y minus f of c, y minus y1 equals m times x minus x1, which is c here, so x minus c. So there's my tangent line going through there. And I wish I picked a different color. I think I can switch colors here. Let's see how to do that. No. Desmos lets you switch colors. Here, there we go. Let's make that green. All right, and then I can grab that and move it. So I can see I've got these positive slopes on this left side, and then as we head over here, it gets steeper and steeper and steeper and steeper and steeper, and then it's having a hard time doing it. Maybe I should zoom in there. So it gets steeper and steeper and steeper and steeper and steeper and steeper. Whoa, what happened? Oh, it vanished, right? We have at 0 trying to get there. Come on, move mouse. Oop. Exactly there. Can't seem to get it to stop in the middle. Ah! But we know if we try to plug in c equals 0, oops, right, we have no slope. It's undefined. So I have this slope that's negative, 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 doesn't exist. And the other side doesn't exist, positive, 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 positive. So the derivative at that point doesn't exist. This is a critical point because I have a negative slope on one side, positive slope on the other side. So this must be some kind of minimum because the function does exist there. I do have the point 0 comma f of 0. Does exist there. So if I move c out of the way, you can see that point does exist for the function f. So there's some weirdness going on there. That weird point is called a cusp, and we'll talk more about cusps in a few sections from now. All right, let's take a look at the questions Kelsey asked about. Let's start with this one right here. Let's blow it up a bit so you can read it. Find the maximum and minimum values of this function on the interval from 0 to pi. So to do that, we start off by finding the derivative. So what is g prime of theta? And derivative of 5 theta is just 5 minus 6. 6 is just a multiple. Derivative of sine is the cosine of theta. Then we set this equal to 0 to find the critical values. So critical values is the next step. So we subtract the 5 over negative 6. Oops. Cosine of theta equals negative 5. Divide by negative 6. Cosine of theta is equal to 5 over 6. And so then one thing I can say here is that theta is equal to the arc cosine of 5 over 6. And I want to figure out what that means. So just some things about the arc cosine in terms of finding these values. The arc sine exists between negative pi over 2 and pi over 2. The arc cosine exists between 0 and pi. So when I use the arc cosine, we're going to return a number in this region right here. So if we look at the unit circle for a minute, and so, and I'm just going to draw the top half, and you'll see why in just a sec. Down here is where theta is 0, right? Theta equals 0. Up here is where theta is pi over 2, and way over here is where theta is equal to pi. And I'm looking at the cosine on the unit circle. Cosine is an x value on the unit circle. So then if this is 1 for x way over there, then 5, 6 is probably about right here. So that right there is x equals 5 over 6. And then, that's a crappy looking unit circle, but oh well. Let's say over here, that's the point. So when we find this arc cosine of 5 over 6, we're getting this value right here. Now, on the unit circle, there's another point down below where x also equals 5 over 6, but that is not in the range of the arc cosine. So here's the first one right there. So I know that that's one of the answers. And then here, let's see, I want to find another point on that interval there from 0 to pi. Here is pi over there. I think x, that's the only one. Is that true? Let's look at the graph. Let's see something here. And just a sec. X value leads to this theta. Yeah, so for the max and min, we got to plug back in. So I've got one x value so far, one theta value so far. So far, I know that something's happening at the arc cosine of 5 over 6. So they claim that there's another one. Oh, right, duh. Okay, so here's the deal. On this interval, there's only one critical value. That's it. The related 0 is not inside the interval from 0 to pi. It's down here at either after pi, so greater than pi, or less than 0. So that's the only critical value I have. However, here I have a closed interval, and I talked about this in the last class. If you have a closed interval, then the endpoints are possible numbers too. So there's 3 things I need to check here for maxes and mins for theta, g of theta. I need to check the endpoints, 0 and pi, and then the critical value I found in between, which is the arc cosine of 5 over 6. So we just need to find out what are each of these, and then one of them is going to be a max, one's going to be a min, and the other is just neither, probably. So now we need to calculate some numbers. So do I have a new screen to play with? Let's make a new screen. And Desmos should work fine here. So all I need to do is evaluate at those 3 points. So let's look at our f of x equals, let's see, what was it again? 5x minus 6 sine of x. Come on. There you go. 5x minus 6 sine of x is that right there. Interesting, that's not what I expected it to look like. Huh. And then we are on the interval from 0 to pi, so I guess I kind of want to see that. X equals 0, throw in some boundaries. X equals pi. So I'm only looking between those 2 lines there. That's all I care about. And I found that, let's call it, I guess I can type x equals the arc cosine of 5/6 is another important thing. And so I can see that down here. So then I want to know what is f of 0 on the left. I want to know what is f of that arc cosine, which I already have. I'm just going to retype it here. Oops. And then what is f of pi? So we looked at earlier that if we have a closed interval, then you could have an extreme value at either end of the interval or in between. And with a closed interval, you're guaranteed, because you can evaluate at the endpoints, that something's happening at an endpoint maybe. So you're always going to have a max or min if it's a closed interval. If it's an open interval, you might have no maxes and mins at all. So looking at these 3 numbers, 0, negative 0.388, and 15.7, I can see that the arc cosine, when I plug in the arc cosine of 5/6, in this interval, that's the absolute smallest number. And then the 15.7079, blah, 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 that's the absolute highest number in this interval. So my minimum is negative 0.38819, blah, 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 and the maximum is 15.7079, blah, blah, blah. And the key is, we've got a closed interval, check the endpoints. So that was it wasn't really a trick question, it was just, that was like the most important part. Was it the second most important part of that section? That endpoints are important too. All right, so, and then the minimum value. So remember, that's the y value. So if I wanted to state it exactly, I can just use that arc cosine. Otherwise, it will probably accept an approximation. So the exact value is just 5 times the arc cosine of 5/6 minus, so I just plug that number into the function, 6 times the sine of the arc cosine. And the sine of the arc cosine of 5/6 does simplify, but we're running out of time, so I'm not going to take the time to simplify that. I'm just going to go for this one right now. We've done plenty of those in the past. So that's one of them, and the other one is when I plug in pi. So 5 pi minus, let's see, the sine of pi is 1, so that would just be 5 pi minus 6. Sine of pi. Yes, that's correct. Ah, what? Did I put those in the wrong spots? Let's see. Pi should be the max, and this one should be the min. What did I do? Pi should be the max. Huh. What the heck? What did I do wrong? Minimum comes from the arc cosine, which is this point here. Why doesn't it like that? I think I typed all that right. Oh, I did arc sine right there. That should be arc cosine. But what's wrong with this one? 5 times pi, the max was 0. But 0 is not the highest number. What? The highest number is up here. Oh, here it's saying it's 5 pi. Did I miscalculate? What did I do wrong there? The sine of pi is, am I losing my mind here? I know my answer hasn't changed. What did I do wrong there? 15.07. Apparently I'm losing my mind. Oh yeah, sine of pi. I'm thinking pi over 2. Sine of pi is definitely 0. Okay, I got my mind back. Thank you. All right, unfortunately we're out of time for fun with math today. So that other question, let's see if I can give you a tip on it. Yes, so the tip on that one right there, when you take the derivative, right, you got to use the product rule and you set it equal to 0, e to the x can't be 0. It's not possible. So then it's the rest of it that matters. So you just factor out the e to the negative 5x in there, and then the rest of it leads to the 0. So e to the 5x can't be 0. It's not possible because that has an asymptote at y equals 0. So that should help solving that one right there. Otherwise, we can look at it next time. All right, you guys. So we are officially what, a day or 2 behind schedule? Let's double check here. I adjusted the due dates either way. Thought we might catch up a little today, but it's okay. Oops, wrong button. Anyway, due dates are okay. Have fun, do good math. I'll see you next time.